Everybody, want to welcome you to the second part of your first labs. This will be Lab 1B, Photoelasticity and Photostress Analysis. Continuing on from what we did in the first part of Lab 1A, Photoelasticity. So we're going to continue on, and what we're going to do is start to introduce some new equipment to this lab here. So first thing we're going to take a look at is the circular polariscope here. So this can produce circularly polarized light. The light source polarizer and the quarter plate on the right, so we can see that over here in our diagram here, and we have a camera analyzer and a quarter plate on the left. So you can see this again right in that image on the right over there. So we'll be utilizing this equipment and introducing it in this week's lab for 1B. We want to take a look at is the reflected light. So as we're using this here, we're looking at objects and seeing how it reflects back at us and looking at the fringe patterns on those objects. So this is the photo stress method that we're going to be utilizing. So one real-world application for this reflected light, we could use this technology when we're inspecting aircraft landing gear during manufacturing process. So we can see here on the right, he's going through and inspecting the bottom landing gear. It's important when we're maybe testing out new materials. The manufacturing process might change a little bit, or just a typical regular inspection after it's been produced. Another application where this could be used is in the biomedical industry here, particular hip replacement where they're putting in a human femur bone. So we can see here on the right, you can see this reflected light over here. Here's a human femur bone in the center here. So you can utilize this as an inspection method as well. So we go back to what we saw in the first lab here. Some of the same type of polarizers, quarter wavelength as well, but now for the circular polariscope here. So we have the basic equation there. Light intensity is given by the following equation where we have I is equal to b squared times the sine squared of pi delta over our lambda. So for our circular polariscope, take a look now. When we're talking about light intensity, we have the equation here that I is equal to b squared times the sine squared of pi delta over our lambda for our wavelength there. We can see our diagram on the right that we've seen before. Talk about our analyzer as our wave comes in through. See a phase shift on the way out. So as we're applying this equation here, our light intensity is 0. Delta is equal to 0. Delta is equal to our lambda. Delta is equal to 2 lambda, or delta is equal to n times lambda, where n is our fringe order. So for a given wavelength, we have the fact that delta is described by the following relationship. Delta is equal to n times our lambda. Now, if we're talking about Brewster's law, we can plug this in here to simplify and reduce this down a little bit. So Brewster's law states that epsilon sub x minus epsilon sub y is equal to our delta over hk here. Plug in our delta from the above relationship up here. Delta is equal now to n times our lambda. So this whole relationship is equal to n times lambda over hk. Again, we can move this around for some of the other relationships we saw before. And what we have here is this is equal to n times f over h, where f is our value, our fringe value. So for an isotropic material, the principal strains to the principal stresses, we come down here to this relationship now. We have our sigma x minus our sigma y is equal to our n over h times lambda over k. Reduces down from the previous relationships there to n times our f sub sigma over h. Now for a given fringe order n and a specimen thickness known to us as h, we can have a wavelength here for white light we know as 22.7 times 10 to the negative 6 inches, or 575 nanometers. From that information, we can back out our f sub sigma there from that relationship above. Talking about reflected light here, this passes through twice through the material. So we can see over here on the diagram on the right, we have our quarter wave plate, our polarizer. Here's our light source right there. This comes down through, light source goes through the polarizer, through the quarter wave plate, comes down here through the photoelastic coating to whatever our test part is over here. And whatever type of, we do have this in the middle here, our reflective adhesive right there. Comes back off of that, goes through quarter wave plate, our analyzer, and then our observer can see that right there as it comes out of the analyzer. So this relationship, H effective, is equal to 2 times H. Our epsilon x minus our epsilon y is given to us by the relationship, the N times F over our H effective there from that relationship up top there. Then we can plug back into this relationship over here. So our sigma x minus sigma y is equal to that N times our F sub sigma over H effective, which we saw from the previous slide there. So there's our stresses and our strains and the two relationships there. So we're talking about photo stress here. What we want to do is relate our stress state to what is visualized. So we're talking about calibration. We have our controlled input, which is the materials testing machine. We have our measured output, which is our fringe patterns, and we have our simple geometry. So we need to have an analytic solution for the stress state. This slide here we have is stresses in a disk. So we have diametrically opposed concentrated loads. We can see we have our loading machine here with a disk sitting in it, and we can see the fringe pattern here in this image. So this also brings up a good point as we're doing labs. We also want to zoom in because a lot of the data we're going to collect is by looking at the fringe patterns. So we don't just want an overall image like this other than to put in our reports as our setup. What we want to do is that we look at the next slide. A nice close-up image of the fringe pattern on the object that we're testing. So in this case here, our disk here. So we can go through and analyze it based on this image later as we're doing our data analysis and processing and writing our report. So we're talking about fringe factor determination. Number one here, settle disk in between material testing machine platens with minimal load. So the disk is going to appear dark. So you're setting it up in the machine there, put the minimal loads on it just enough to hold it in place. Then you're going to apply displacement until the first fringe appears and reaches the center of the disk and record that applied load. Then we'll repeat to record loads for each of the first 5 fringes. So the next thing we're going to want to do is plot our load P versus our fringe and then perform a linear fit to solve for our F sub sigma. So we can see we have our relationships down here relating our F sub sigma and our load. From the previous equations, we can rearrange whether we're solving for F sub sigma or for our load P there. What we can do is we can come over and when we plot this here, we can see on our x-axis we have our fringe order, on our y-axis we have our loading in newtons over here. And so for each of these, for fringe order 1, we have a value to plug in there. For fringe order 2, we had a value for our load that we can plug in there, 3, 4, and 5, and so forth. And from that, we can do a linear fit to this. And we can pull out their statistics here. And this can be done right within Excel. You can do it in MATLAB or Python as well. But for something like this, Excel might be the quickest, easiest way to plot this data and get your linear approximation and your statistics out of that in order to solve for this F sub sigma. So from this image, we can see here, we have 5 fringes are shown. So you got fringe 1, 2, 3, 4, and 5 there. We can draw a line across the center of the disk right there and measure the distances between our x's. So you can see these distances are measured there, 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 and there. So next for our fringe factor determination number 2, what we're going to do is plot our fringe versus our x over r. So we can see down here on our x-axis, there's our values for x over r, starting at a negative 0.8, going all the way up to a 0.8 with our 0 right in the center. And on our y-axis here, going from 0 to 5, we have our fringe order there again. So now our fringe order is on our y-axis there. We have fringe order 1 and our x over r value here. So we can plot all of those right here. Again, MATLAB, Excel are both acceptable ways. Something like this, probably an Excel chart, is going to be the easiest way to plot this. So to compute F sigma for each pair for our N and P, we have the following relationship shown here, where we have our F sub sigma is equal to 4 over pi r times our P over N times our H effective over H times, now in brackets over here, we have our 1 minus x squared over 1 plus x squared quantity squared. We can use this equation now here for F sub sigma. Next, we're going to talk about disk fracture. So if we can see here, there's our disk. We can see our fringe lines there. Then we have a disk here, and you can see that fracture right along this line right there. Separate that out here. So once we apply that load, we do see we have this fracture here, split this disk right down the middle, essentially, right there. So now if we want to talk about stress on these discs here, we have this diagram on the right over here. We have our origin at the center. We have our x-axis acting in this direction, our y-axis going up in this direction here. You can see our radius given to us by d over 2. Now we have the location here of this point right here, where we're taking our sigmas, our stresses at this point. This is some distance x from our origin, some distance y from our origin here. We can see we have these angles theta 2 and theta 1 right there related coming back off of our vertical line over here. Now, if we're talking about calculating our stresses, we can have our sigma x, our sigma y, our tau xy over here. So we have the following equations. We can go through where each of these variables relates back to our given diagram. A lot of these will be known or measured values that we can plug into this here. This relates over here. We can see now our element that we're dealing with here for our sigma y with this relationship here, our sigma x, with our sigma x there, and our tau xy right there with this equation over here. So look a little bit further here. If we have at the position where our y is equal to 0, we can then simplify down these equations for our sigma x, sigma y, and our tau xy. We can see our element up top here. Again, there's our sigma y, our sigma x, and our tau right there. So we can relate, again, these back to our diagram that we can see here, as well as these three equations based upon the fact that y is equal to 0. Now our x asterisk here, our x star, that we see in all of these equations, right there, are the relationship of our x over r. So that's where we get our x star from. Simplify this equation down essentially by just calling this ratio between our x and our r, our x star right here that we can plug into all of these. So for the special case now where we have x is equal to y is equal to 0, so our x and our y are both equal to 0 here, these again can be rearranged, simplified down now to the following relationships for our sigma x, our sigma y, and our tau xy there again, still related to our same element over here and our plot that we see over here as well. If we reduce these down, what we can see now when we plug in here, our sigma x reduces down to this here, our p over pi rh, and our sigma y reduces down to a negative 3p over pi rh. And again, this is still for that same relationship here. This is equal to our x over our r value. So for this disk here, we have the difference of sigma x and sigma y. We take the difference between those two equations right there and subtract them. Come down and we end up with this relationship right here. So our sigma x minus our sigma y is equal to our 4p over our pi r h times now our 1 minus that x star squared. Again, that's our x over our capital R there. All divided by 1 plus x star squared again. So we've seen this relationship before. This is our difference between our sigma x and our sigma y. So now we want to plot this here. So we have this relationship, our sigma x minus sigma y is equal to our 4p over our pi rh times, again, our 1 minus x star squared divided by 1 plus x star squared, again, where x star is given by this relationship here, x over r. What we can do now is we can take this right here, divide both sides by that, over here multiplying by the reciprocal of it, when we bring it over to the left side of the equation here. So now we have this relationship that was shown here. From that now we can plot, if we can see, we have our x over r down here on our x-axis going from a negative 1 to a positive 1 over here. And on our y-axis we go from 0 up to a 1 there, where our disk center is right at the peak at the dead center of our x over r here. So again, how we want to plot this. MATLAB might make a little bit more sense to do out these equations, do the plotting here, but it can also still be done in Excel or Python as well. So the next thing we want to do is solve for our fringe factor. So we have all these relationships and equations that we can plug in. So we can see we have our sigma x minus sigma y is equal to our 4p relationship here, where we now know from from previously that our sigma x minus sigma y is given by this relationship here, n times our f sigma over h effective, and what we're looking for is our f sigma, so we want to solve for that, so we can plug this in over here into this relationship for our sigma x minus sigma y. We do that, we end up with this relationship, when we plug this in down here, this now, you can see that there to replace that, end up with this relationship there. Reduce, simplify, we end up with solving this for there, so we can then multiply our n over, or sorry, divide our n over to the other side, where we see that right there, and we can multiply our h effective over the other side, which we see right here. We end up with this whole relationship for our fringe factor f sub sigma. So now we can see again, image of our disk with our fringe patterns all numbered here. So in summary, at the point x equals y equals 0 of a disk in compression, we have this general equation we've just solved for here for f sub sigma. Now, again, when we're talking about at x equals y equals 0, we can reduce it down and simplify it here to f sub sigma is equal to 4 over pi r times our p over n times our h effective over h. So the next thing we have here is our supplementary slides. So these slides here, I'm just going to go through these pretty quickly for you. You can look back through these. A good way to relate back to these general equations for specific applications as you're going through. So in this case here, we have two methods, two relationships. You have your factor at the center and your factor across the middle for these special cases here. So we can see the associated equations you can reference back to in these slides for both of those two cases for fringe factor determination. Again, for a disk here, you have a stress at some point. We know the x and the y location of that point on the disk. We want to define the state of the stress for geometry, define the boundary conditions, and transform the desired coordinate system. So at this disk, you can see the element right here. We zoom in on that. We have our stress element here. We have our sigma x, sigma y, and our tau x, y there. We can zoom in a little bit closer on some of these angles. It's a little bit easier to see now that this is a little bit bigger. So we have this relationship here. We pull that out. Come over here, zoom in on it, see all of our variables associated with it. So as we're dealing with a disk here, we have two radial compressive stresses. The first one that we're going to talk about is our R prime. Now our R prime, we can see is given in terms of this relationship here, that 2 times P times the cosine for theta 1, which we can see up by our theta 1, we may need to do a little trig to break this down in terms of its components there, is equal to a negative sigma r prime times our area, where we can plug in for our area, and we can use our h value, you can see measured here from our point over there. We plug in here, we end up with this is equal to a negative sigma r prime times now, we plugged in for our area term over here with our h value right there. So we can rearrange this a little bit here, and we can see that 2p times the cosine of theta 1 from our left side of our equation is equal now to this negative sigma r prime times our pi hr1. Solve this now for our sigma hr1 is equal to, now when we arrange this, negative 2p over our pi h times our cosine of theta 1 divided by our r1. So that's for the first. So recall there were two radial compressive stresses. So we just went through and solved it for our sigma r prime. And that was given by this relationship here. Now we want to solve it for our sigma r double prime over here. And that's given by this relationship down here, which is slightly different, where the difference is our r1 and our r2, which we can relate back here. Here's our r1. Here's our R2, one coming from the load at the top, one's coming from the load at the bottom for that distance there. So at a point on the surface, we can define here our sigma r double prime of theta 1. We can see here we have to do a little bit of trig over here. We come out to this point over here now where our p is over there. You can see our theta 1 and our theta 2 coming off from our top load and our bottom load over there. We see this relationship now given to us that our sigma r double prime is equal to negative 2p over our pi h times the cosine of theta 2 over our r2, where we have this relationship here that our theta 2 plus our theta 1 term is equal to our pi over 2. So we can rearrange that, solve this for our theta 2, so theta 2 is equal to pi over 2 minus our theta 1. So we can now plug this relationship for theta 2 back into our equation we have up top there for our sigma r double prime, and we end up now with this equation here. This equation can then be reduced a little bit further and simplified now to see that this is equal to 2p, negative 2p over our pi h times our sine of theta 1 divided by r2. So if we're talking about a disk here, we want to find the normal stress at the surface. What we have here is our sigma sub n. At this point here, we can see there's our distances relative to our two load points. And if we want sigma sub n, it's the square root of the sum of the squares of individual components. So there we can see, okay, there's that component there, right here. There we see this component here from our double prime term right there. So there you go. Right triangle. A squared plus b squared equals c squared, so we can do that right out there. We can locate this by the square root of the sum of the squares to get our sigma sub n. So again, where our equations for our sigma r prime and our sigma r double prime are given by these relationships here. So plugging those guys into that above equation here, sigma sub n term for those two parts there, plugging those equations in relationships. We can simplify that down, reduce it, and we end up with this relationship here now for sigma sub n. Again, we can still reduce this a little bit further. We end up with here, for this case here, is equal to negative 4p over pi hr. So what we want to do now is look in terms of components. So if we're talking about our sigma x, we can see up here, on the top right, we have our sigma x term here. It's given by this relationship here, but everything we've done so far has been relative to this sigma r prime and sigma r double prime term over here. So we need to break it back in there. And the way to do that is with trig. Trig is going to be based upon these angles, our theta 1 and our theta 2, that got us down into this coordinate system for these guys here. And we need to relate these back now to the sigma x and the x coordinate system here. So we can do that based upon this relationship. We have our sigma sub x is equal to this equation here. Again, based off of our sigma r prime, our sigma r double prime, and some trig based off our theta 1 and our theta 2 angles. So that being said, we can plug in terms of our sine of theta 1, cosine of theta 1, cosine of theta 2, and our sine of theta 2 based off of these relationships here and where they came from. So we can plug all of these relationships back into this above equation right here. When we do that, we end up with this equation down here for our sigma x based on all that. And that eliminates all this theta 1, theta 2, theta r prime, theta r double prime are now all eliminated from that there. And it's now in terms of our x's, our y's, our r's, our external load p, and our h values there. So we can plug this straight in now from some of the known values that we may have in order to solve for our sigma sub x. So at the case where y is equal to 0, we can see here if y is equal to 0 here, then our r1 and our r2 would be equal. So this is equal to, as we can see, the square root of x squared plus our r squared. We have this relationship here. Plug into this here. We see that our sigma x is given by this relationship here. We can then reduce and simplify this down. We end up with this relationship down here. It's equal to negative 2p over pi h times our 2r x squared over x squared plus our r squared squared minus 1 over 2r, which again, we can still reduce this down a little bit further, pull our 2 out front here, and we have this relationship shown here. So from there, we see again, so y is equal to 0, we have that relationship that we just showed from the previous slide there. What we want to do next is to normalize our x. So we recall our x asterisk here, our x star is equal to x over r. Plug this into our relationship down here for x over r. We end up with this equation now for our sigma x that we see here. So the last slide here, we'll plot vertically based upon this relationship that we just saw there, this equation we had from the previous slide for our sigma sub x. We can see on this plot over here where we have our loads on the edge of each of the disks here. Our P and our P there. There's our x-axis going across this guy here. Like this, there's our origin at the point of the center. There's our sigma sub x right here as we plot it under this curve there.